Okay, in part three, this video we're going to talk about modelling sediment budgets within a river basin. So this falls within the topic 6, sediment transport of natural channels module. Now remember this fluvial system here, which gives the three zones within a river catchment. We have the sediment production zone, the sediment transport zone, and the sediment deposition zone. So typically within the sediment production zone, we are supply limited because there's erosion occurring, and the amount of sediment that's transported is dependent on how much erosion has occurred, either at the site or in the upstream catchment. In the sediment transport zone, the supply roughly equals transport, and so it's transport limited. And in the sediment deposition zone, supply exceeds the transport capacity. So again, it's transport limited, but we get deposition. So that's a general pattern we get across these three zones. So if we really want to understand sediment loads within a river, we actually need to think about this whole fluvial system, the supply, transport and deposition zones, and probably need to think about modelling sediment loads for the whole river basin. So we know when it's supply limited and when it's transport limited, and when the supply of sediment exceeds the transport capacity, and we're likely to get deposition. This kind of river basin sediment budget modelling is really in fairly early stages. It's developing. We're developing our capacity to do this. CSIRO in Australia has developed a model called the sediment model, which has now been used quite a lot in Australia to model sediment budgets, sediment loads across a whole river basins. And the way this kind of model works is to divide your catchment up into a set of hill slopes. And it works out what the sediment is supplied from those sort of hill slopes or sub-catchments into the river network, which is represented as sort of a node link network. And then it routes that sediment on downstream mathematically to the river basin outlet and either erodes or deposits sediment along the river network, depending on what the transport capacity is and the supply of sediment is to that particular link in the network. Conceptually, how the model works in each link within the network is it models the main sources of supply of sediment to that link, which is the riverbank erosion from gullies within the catchment. So gullies is quite a common feature in Australian rivers, which are large sources of sediment, or have been historically at least. It models inputs of sediment from upstream, and this is for the bed load. And then once you've got those inputs, it models the sediment transport capacity, and if the sediment transport capacity is less than the amount of sediment being supplied, you get bed load deposition, and then it represents the remainder that gets transported on downstream, and so on for a whole series of links all the way through to the catchment outlet. The suspended load budget is very similar. It just also includes a hill slope erosion term. So we have a smooth hill slope, you're getting some fine sediments coming off that, and that contributes to the suspended load budget. Here's the results for applying this particular model, SEDNet, to the Murray-Darling Basin. It shows the suspended load in kilotons per year throughout the whole river network, and so we see gradually increasing sediment loads as we move downstream, with the highest sediment loads here in the Murray River and at the mouth. A fairly typical pattern one might expect to see. But this is a modified catchment. It's highly disturbed, and all those disturbances have increased the amount of sediment being transported within that catchment. And this is the same model applied to the Murray-Darling Basin, but it shows the sediment loads prior to European settlement, and so they're much lower. We can see really low sediment loads throughout the whole of the tributary network, and really only increasing within these major rivers. I'll just flick back to the other one, and you can see all these sort of tributaries through here. The sediment loads have increased substantially, and in the main rivers as well. And over here we can see the ratio of sediment load currently, as disturbed, to the pre-European case, and where it's purple, the ratio is greater than 100. So we've had a 100-fold increase in sediment load in those particular rivers. What's interesting is that the sediment load hasn't increased at the mouth of the river. So in the lower Murray River, the sediment loads are almost exactly the same as they were pre-European. I'll come back to that point in a sec. What this shows is the bed load deposition. So where the supply of sediment to a site exceeds its transport capacity, the sediment's deposited on the bed of the river within the model, and this shows the amount of sediments deposited. Where it's red, the deposition rate is at 1 metre per 100 years, so the bed of the river would increase by 1 metre over a 100-year period. And we can see all these rivers along the base of the Great Dividing Range. The Great Dividing Range goes along on the catchment boundary on the east and the southern boundary of the Murray-Darling Basin. And as the rivers flow out of the Great Dividing Range inland, all this coarse material is being deposited on the bed of the river. So this is coarse material that's been eroded as a result of human disturbances is being deposited within the rivers. And that explains why further downstream sediment loads are largely unaffected by human disturbances. The additional sediment that's been eroded from the catchments is being deposited in the foothills of the headwater zones, and effectively that's buffering the lowland river from these catchment disturbances. So you see very little change in the sediment loads down the bottom end of the river system.